Thank you very much. Thank you for coming to this invited keynote presentation by James Kuffner. It's a great pleasure to have you here, and it's also a person with a kind of remarkable CV. He actually got his PhD from Stanford and then moved to Carnegie Mellon and being an associate professor over there. He's still associate professor at Carnegie Mellon. That's what I learned. That's where he also developed his techniques for path planning and also manipulation planning. This is actually work that James Kuffner is very well known for, and he's produced a lot of papers in this area and also influential papers in this context. He received the Okawa Foundation Award for Young Researchers in 2007, and in 2009 he went to Google and joined the self-driving car team, and later on became co-founder of the Google Robotics team. And today he's going to present his view on a cloud-enabled Shakey to us. Welcome, the stage is yours.
Thank you, Wolfram, for the kind introduction, and thanks the organizers for allowing me to speak to you today. I think this is a wonderful celebration on the half-century legacy of Shakey the robot. And when I thought about what I could talk about today, I wanted to reflect upon the impact that Shakey has had on my own research career and also what I see as promising directions for the development of intelligent robotics as we live in an era of cloud computing and the fact that we're all carrying around in our pockets computing power that's equivalent to the best supercomputers just a decade ago. So I've looked at imagining a cloud-enabled Shakey as my first talk. How do I actually... This one? No. That's fine. Oh, can you see? Okay, good, excellent. So in reflecting upon Shakey's legacy, I think the important point is that it provided a design pattern for an intelligent robotic system, and that includes a vertically integrated system of subcomponents all the way from motor controllers, sensors, low-level controls, and up to the highest level strip-based task reasoning, which was really impressive for the time. And this led to a design pattern that has been used ubiquitously in robotics over the last half-century. What really got me excited about robotics 25 years ago when I started thinking about these problems is the idea of search-based artificial intelligence. In 1989, I joined Stanford and started looking at thinking about how could we build computer programs that could compete at the level of humans. Then, of course, in 1997, it finally happened where Deep Blue defeated Garry Kasparov. But what was interesting to me about the way that the machines solved these problems was that they could do planning in the sense that they could reason about the consequences of actions. And of course, you know, Deep Blue might examine 200 million chessboards per second. And that wouldn't be the way that a human would solve the problem, but it sure is effective. And so my thought was, how can we leverage and build computer programs that enable robots and computers to exploit the skills that they're good at and maybe have humans fill in the gaps or things that they're not good at. So I think when you think about a game where it's very discrete and there's no uncertainty, if you think about planning in the real world, you have suddenly this very complexity that rears up in terms of the models that you're using. You have uncertainty both in the sensing and in the control side. And then, of course, if you're trying to plan in the space of actions for something like a whole body humanoid where it has to balance and grasp and make contact with things in the world, you suddenly have this very continuous and high dimensional search space, and it all has to run in real time so that the robot doesn't fall over. So suddenly you get this snowball of complexity that happens that I'll talk about a little bit later. I started looking at humanoid motion planning with the various robots around the world, and one of the efforts that I started looking at initially was autonomous grasping and manipulation. So I'm going to explain sort of how the planning in the A-star search that was developed for Shakey influenced a lot of the research and planning that my group at CMU got involved with, and things that I'm still interested in. So I worked with my colleague Steve Laval to develop a sampling-based planning algorithm called an RRT. And the goal of this was to connect in a high-dimensional space very quickly, find a solution, even if it wasn't optimal, so that you could actually use it, and you could basically make a planning system that was tractable for higher dimensional systems. This actually became useful to solve one of the benchmark problems, which is the alpha puzzle here, shown here. I'm not sure why the movies are not playing. It's rather unfortunate. Just see if I just do this way. I wonder if it works. Here we go. Okay, sorry. So one of the trade-offs here was that we wanted to be able to make the common case fast and have a computation that was balanced between exploring a space and rapidly converging on a solution. So that led to this experiment in trying to implement this online on a robot for manipulation. So here we have a stereo vision camera in the head. We will compute a path in the 7-dimensional space of the arm to grasp the bottle. That's collision-free, so it computes the grasp, and then it's able to compute another path. And then you have a beverage delivery system that is very expensive. Now, of course, this was mostly, in some sense, trying to prove a concept that we could build a system that was adaptive and dynamic, and I think that was in the spirit of Shakey. The Shakey was able to not just perform pre-programmed tasks, but actually do dynamic tasks. So a lot of my students continued on this work, putting in constraints like regrasping, and one of the things that we looked at was how can you actually search in a space to find stable grasps. And this is where I think cloud computing can also help find solutions. You can build these simulations that can run in a distributed manner, and then once you've found stable solutions, you can remember them and then recall them for future use. So this became integrated, and I would say a Shakey descendant, which we built at Carnegie Mellon's Quality of Life Technology Center, which was called the Home Exploring Robot Butler. It was a wham arm and a hand on top of a Segway base, and we used a laser scanner to navigate and also to sense obstacles. We got it to the point where we could integrate a lot of different systems, including recognizing objects, computing a grasp, planning an arm motion path, and then verifying that the task has been completed. And what inspired us was a lot of work that had been done in the conference like ICRA and Humanoids in putting together systems that will scale to many objects, systems that will scale to many situations, and not just have robots in factories playing back pre-programmed motions. And one of my students, Dmitry Berenson, also looked at planning with constraints, so that way you could look at if you want to keep something vertical, or if you want to respect the fact that you have limited torque and you need to move a heavy weight, how can you do it in an advantageous way? And my other student, Rosen, his PhD thesis, I think, built on a system that looks much like a lot of the subcomponents of Shakey, in trying to build a series of sub-goals that are generated and then integrated with perception and feedback and planning, and building a kind of robot knowledge base. By the way, each of these tasks are mostly open source as part of the open source Robotics and Automation virtual environment, which is a version of the software that I had built when I was a grad student and is now released to the open source community. And Rosen is here today. He has a company now and founded a company around using this planning technology for automation called Mujin. You should check it out. So one of the other things that we wanted to do was have manipulation, but we also wanted to have navigation. And searching for navigation in the Shakey world was building a map and then exploring discrete cells. But if you did that in a 2D grid, it would mean that your robot always had to circumvent obstacles. Whereas if you had a legged robot, you could actually step over or step on obstacles if you needed to. And so the thinking was to try and figure out a search-based framework for doing navigation for legged robots, so we came up with this concept of footstep planning, and Joel Chestnut, one of my first PhD students, who now works at Boston Dynamics, developed this technique. And this is sort of one of the first videos that we built with our colleagues at the University of Tokyo, at Professor Inoue and Unaba's lab, where we had onboard stereo vision. We would build a map, we would plan a path towards the goal. In this case, it would detect the red ball, and then it would plan online a sequence of footsteps to navigate to the goal. And this first version of the footstep planner could examine a few thousand footstep candidates in about 3 seconds. But very soon we were able to upgrade the computers, and the joke in motion planning is that you can republish your research 10 years later with the title Real Time. Just let Moore's Law do all the hard work. But this is actually replanning from scratch every footstep cycle. This is a 1,000 millisecond step cycle, and it's be able to replan from scratch where it is. So when there's small uncertainties in the execution, it's able to replan. That culminated into what we call ASIMO and the Pink Blades of Doom, which was an experiment we conducted at Carnegie Mellon, several of my students. And the goal was initially to, since we didn't have access to the controls of the Honda controllers, but what we could observe that it was deterministic, and we could build essentially a motion map for how to control it and how to move it, we were able to basically run this planner. This has an 800 millisecond cycle, and it can also plan in both space and time. So if you have predictable motions, we could have online tracking of the obstacles. We called this ASIMO Plays Frogger. This shows an example of the online search, and by this time we're searching upwards of 10,000 states in one step cycle. And there's my student Joel. He's able to have the goal location moved around in real time. The robot's tracking it, and it's constantly replanning and trying to avoid stepping on the red areas. And the poor robot just keeps getting tortured. Now, what's interesting is that we were able to deploy this on several different robots. It's the same planning framework, similar to A-star search. Here, we're actually estimating in real time the rotational velocity as well as the position, so that we can plan in space and time. So this would be like the robot trying to go through a revolving door. And so this is actually what the robot sees, in this case, in off-board perception. We're able to track and estimate. And because we can estimate where the future positions of the obstacles are, of course, we can build this plan. This is actually pretty tough for a human to do. I remember trying to do it myself and stepping on it many times. This was deployed on other robots, and I just wanted to point out this is Joel working at AIST lab in Tokyo, in Odaiba, And we built a virtual reality interface to control the robot so that you can actually see overlaid on the real world the plan that the robot has actually computed. So you can see he just drew a path on the world saying, I'd like the robot to go here. The heuristic is modified to try and stay as close as possible to the plan, but then you can sort of see in real time the robot providing feedback as to what it's actually planning to do and then executing, and it replans from its current position as it gets to the goal. And you can see actually from what it looks like from the operator view, I think that with the new research in virtual reality and augmented reality, this could be some very compelling user interfaces. Here it's actually stepping up on an obstacle. I think I kind of like this interface because when you have full autonomy on a robot, it'll surprise you if it does something unexpected. And so here you actually get a little preview of what it's planning to do, and you can actually stop it or have it replan if you don't like the plan that it's chosen. My student, Matt Zucker, started looking at dynamic actions. These are things for like Little Dog for the Learning Locomotion program that was part of DARPA. And I'll just play these here. What's interesting is you could imagine some of these dynamic actions as nodes in a footstep-like plan. So you could imagine caching some motor control policies that then you search for. So you could sequence together these motor primitives and then have them executed online. I have another student who, Mike Stillman, unfortunately passed away last year, but he actually looked probably at levels of planning that were most similar to Shakey. He looked at manipulation and also navigation among movable obstacles. And the idea was if the robot has a navigation goal that is currently obstructed, can it actually proactively move objects out of the way in order to clear a path? And so the object becomes something that's movable. So if you have a mobile manipulator that can actually move obstacles out of the way, you can actually solve this problem. So we built, and Mike had built, and some of his students, I believe, are here presenting at the conference, systems that are related to trying to reconnect the AI task planning with the lower level motion and geometric planning. So we learned a lot of things during that research, and one of the things that I kept scratching my head of after all of this hard work was, when are we going to have an intelligent robot personal assistant? And I tried to think hard about what was it that is so hard and why after half a century we still don't have what we had hoped Shakey would result in, and that is some intelligent robot we could buy right now. And I like to call it a research challenge snowball, and I think it actually comes from the unstructured environments. So because we have unstructured environments, we have unknown objects, unknown obstacles, it means that we have to use online perception. And that means we can't really cheat with a priori models when you have unstructured environments. That also means because you have to do online perception and things may move around in the world, you can't use predefined trajectories. So that means you have to have online motion computation. And finally, you might have dynamic tasking because you can't rely on predefined sequences in all cases. And you may need to restart if one task fails or recompute a task plan. So because you have to build all of these things and solve all of these problems, I think it has been very, very hard. And these problems still exist, but what I'd like to argue is that we are now poised, I believe, to start solving many of these problems. And I left academia and in 2009 felt that, okay, I'm going to try and stimulate the industry. I joined the Google self-driving car team, and I founded a project involved with 3D scanning at Google, and then founded the Robotics project. And one of the things that was exciting to me at the time was thinking about what would change for a planning system if you had suddenly a massive distributed computation available as a resource. So back in 2011, we built a library and open sourced it so that you could turn any Android phone into a little robot. So every Android phone since Froyo, you can plug in a USB board, and then you're able to control cameras. You can have motors. You can basically build your own cellbot. We also, some of my colleagues at Google, created a native implementation of ROS on Android that they also open sourced. And what was interesting to me was that people were turning over cell phones at about an 18-month clip. So that means every 18 months, people were basically handing a supercomputer to their kids because they didn't know what to do with their old phone, or they were selling it on eBay for 10 bucks. And so the thought was, well, wow, you could actually build a robot out of this because it has most of the things that a robot wants, like GPS, like an accelerometer, like 2 cameras, like a microphone, like a big screen, like a battery, like a GPU, like CPU, memory. All these things it already has, Wi-Fi, Bluetooth, 3G. So the thought was that can we use all these old recycled phones to make a whole bunch of robots that are cost effective. And I think what's enabling is actually wireless networking. I mean, a lot of people talk about Moore's Law as being a revolution in computation, but if you look at peak mobile broadband speed growth in the last 10 years, it's 1,600 factor. Nobody would believe 10 years ago that you would be able to stream HD video from YouTube to your phone and that everybody could do that all at the same time. That's really remarkable. So when we think about the benefits of cloud robotics, one of the things that is exciting to me is having a shared knowledge base. There's a repository of information on the world, like Wikipedia, that we use all the time to access information. Imagine if we can unify that information in a format usable by robots. And the Robo-Earth project and RoboHow and some of those other efforts, I think, are really helping to try and build some infrastructure for that. The other benefit is that we can offload heavy computing tasks to the cloud. So that means you get a virtuous cycle between cheaper, lighter, easier to maintain hardware, just like a PC desktop versus a thin client. If your robot doesn't need to carry around giant hard disks or giant CPU resources, you can actually have a lighter and smaller robot that then needs a smaller battery. And you need less software pushes and updates, and all the hardware upgrades are invisible and hassle-free. And finally, I believe that with many, many robots that are connected to the cloud and able to upload logs of success and failure, we can actually stimulate machine learning research, because now we suddenly can have a lot of the performance in a supervised training data set available to actually learn and make every robot better and more capable. So by data mining the history of all of these cloud-connected robots, I think we can actually make a lot of progress. So I'm going to talk about some existing API services that are also related to this that many of you are used or are actively developing. So for example, I think unquestionably the progress in speech recognition and translation has really blossomed in the last 10 years. It's not so much that the algorithms have gotten better as they have, but the availability of data and the scalability of data has enabled these learning systems to really, really do well and start to, I mean, there's the point now where we can support 80 languages in Google Translate. And now we can actually do speech-to-speech that's cloud-enabled in real time on your phone. So if anybody ever tried this conversation mode in Android, it's very interesting. You can speak to it in English, it'll reply in Spanish, and then in real time, the person can reply in Spanish and it'll speak back to you in English. So you get the Star Trek communicator. It's very, very cool. Not quite the 6 million languages of C-3PO, but we're getting there. Google also worked on Google Goggles. It's cloud-enabled object recognition. And one of the new features that they launched in the Google Translate app, which is free and available on iOS and Android, is also image-based language translation. So you can just point your camera at a sign, and if it's in foreign text that it recognizes, it will real-time overlay the translation to the text. It's very, very cool. You should definitely try it. But what I'm imagining is that at some point a robot should be able to take a picture of something it doesn't understand and upload it to a knowledge base and then be able to recognize it, download semantics, usage instructions, maybe mass, model, material, friction properties, etiquette to use that object. and domain knowledge, and those should be naturally available to a robot. So one of the collaborations we had with Ken Goldberg and Peter Beal and his group at University of Berkeley was to try and install this on the PR2 there. And we could recognize objects, pre-compute grasps, and then leverage cloud storage to download those grasps when it recognized those objects. So this actually leads to this concept of robot sourcing. So human crowdsourcing can scale these hard semantic and control problems globally. But imagine if we have a large-scale deployment of data-sharing robots. It offers very similar advantages to human crowdsourcing. And so that I'm quite excited about. This, of course, also is related to maps and planning. Google has arguably created the world's most detailed 3D maps of the world stored in the cloud. But you can also now sense in 3D on small devices like the Project Tango, which is trying to push together. You have cheap depth sensors like the Kinect and others that are coming out to enable much more rich environmental information. And that means robots should be able to keep those updated so that a robot doesn't have to always, it's the problem with your car navigation, right? You have to go buy a new CD every time there's an update. And finally, I think skills are something that should be transferable. We should have an app store for robots. Tasks and objects and domain information should be able to be translated into a library of skills that are reusable. And the example I always like to use in my talks is from The Matrix. I really like the idea of a robot being able to say, hey, I need a helicopter pilot program, be able to download that. Finally, I'd like to conclude with sort of Google Now. This is, there's a lot of companies that are investing in this, but it's more than just the answers to factual queries, and it's now powered by the knowledge graph. So it's interesting that Google has gone from a company where we had 10 blue links, where we would give you statistically what the PageRank algorithm would decide is the most relevant information for a search, but then we started to look at more curated information. So instead of having for you to click on the link to get the information, we can try and provide it to you. And so we're curating this large database of facts, and we believe that this could also make robots, this should also be available to robots. So you can kind of think of Google Now as the kernel of a small brain of a robot personal assistant. So finally, let's look at some observations. I think right now, big data and deep learning are powering amazing advances in speech and translation. A lot of companies are competing in this area. Standard data sets like ImageNet are really increasing the ability to do object recognition in real time using CNNs. And one of the questions that's open is, are we approaching the critical mass in terms of memory, storage, and compute resources to mimic the capabilities of a human brain in this area? It was mentioned in the forum that a lot of the deep learning has been applied to perception, but it'd be really exciting to apply that to motor control. And now that I know there's several groups here that are presenting papers that are in that area, which is very exciting to me. And finally, I kind of see this pendulum swing between planning versus learning. And it also goes in the area of embedded versus server-based. In the early days of computing, you had the most powerful big iron, and you had dumb terminals. And then the PC era meant that suddenly all the computing was local. And then you went to the web, where a lot of the server-side apps were, and now we're in the era of mobile, where a lot of people are actually going back to client-side computing. So we're seeing this pendulum shift in the areas of embedded versus servers, and then planning versus learning. When a lot of people ask me, well, what's the difference between planning and learning? My personal opinion is that it all comes down to search, because at the end of the day, a learning algorithm is doing optimization. And an optimization is basically searching a high-dimensional parameter space and trying to minimize a cost function. So you can actually wrap them down into the very, very similar functions at the lowest level. So compared to biology, we've actually got an estimate that there's 100 billion neurons in the human brain with 10 to the 15, that's a quadrillion synapses. And I believe that we can reach that storage now, that amount of storage now using a distributed computer. And you can see how that compares to other animals. I think these grand challenges, so now let's say a desktop PC even, you might be able to store with 64 gigabytes of RAM, depending upon how you cleverly encode the connections, you might be able to actually store a net of that size. So maybe something, not quite a mouse, but maybe approaching the intelligence of a mouse even on your desktop. Finally, I think these grand challenges are very exciting. There's a lot of interest and enthusiasm around the Amazon Challenge and the DARPA Robotics Challenge, which will be held in California next month. And these are all very great. I think we should have more of those. I think that definitely stimulated many of us to work on self-driving cars with the Urban Challenge, and these things get the general public also excited about the potential for this technology. So if we think about rebooting Shakey in an era of cloud-enabled computing, I think vertically integrated systems, the time is ripe to reconnect the AI task planning and motor control. That was something that Shakey project did really well and admirably for the time. Now we have so much more computing resources, we should be able to do much more exciting things and have robots that truly can react in a dynamic way to tasks. I believe that cloud robotics enables cheaper, lighter, and smarter robots. We can offload a lot of the heavy compute things and a lot of the data storage to the cloud, and then have enough local computing client side to keep the robot safe and functional. So the way I like to say it is, it's much like your phone. When your phone doesn't have a data connection, you can still use it, it's just not as useful. And that's the way I view a cloud-connected robot. A rapidly evolving infrastructure already exists. There's many APIs that are already available. You're welcome to use many of them. Many of them are provided for free up to certain limitations in terms of traffic. If you create an app that uses lots of traffic, that's good. And everybody can share in the benefit of that. A massive computing resource is available now for deep learning, and I think this is very exciting. A lot of people are excited about it, but we do need data, and I think that's one of the challenges. And so looking at how we can leverage these in more domains for the robot, particularly motor control, will be really interesting. And finally, I think if we can create a shared knowledge base for these robots, that we will be able to enable the robot revolution. Robot experiences and user interactions and learned skills are going to be something that we'll be able to transfer between robots. I have 4 kids, and each one of them has spilled milk probably 100 times over their lifetime. Wouldn't it be really nice if you could train one robot not to spill and then transfer that program to every robot, so then every robot doesn't have to spill anymore? That's one of the benefits. So I'd like to thank all of my students and collaborators who worked on all of this, and of course my colleagues at Google for all of the support and ideas. Thank you. I know everybody's eager to go have dinner, so but maybe we have time for questions.
Yeah, thank you, James, for this very inspiring talk. The vision, your view of the history of robotics and your history, and also the connection to ongoing developments. I think we started a little bit late, and I would be open to have 2 or 3 questions. Please use the microphone. There is a switch. I don't know whether it's switched on.
Hello, can you hear me?
Yes.
Thanks, it was a great talk, James. I wanted to get some comments on latency and reliability. So you said that your phone works even when it doesn't have the data connection. So how do I decide what tasks can be offloaded to the cloud versus not based on the latency requirements or the reliability that I need for that application?
That's a very good question. So I think a rule of thumb for me is any safety critical function of the robot needs to be on board. Anything that doesn't have strong latency requirements. So a real-time system, a safety critical system, all has to be on board. But for example, speech recognition, if I speak to my robot in Spanish and it doesn't recognize me in 800 milliseconds, instead it's 900 milliseconds, maybe it's not that big of a deal. But if the robot's balancing, obviously it has to maintain real-time performance. So I think you have to decide which components of the system are safety critical. But basically there's many useful functions that are not safety critical that can tolerate some amount of latency.
And what are the order of magnitude of latency that you can expect in cloud robotics today, and where do you see it going?
Well, I don't know about...
You don't have to answer it in terms of the... It would probably scale with the amount of compute resources, but I'm just curious.
Yeah, a data point would be like Google Now's real-time translation. The goal is to have, within under a second, a turnaround time of, that means the phone has to detect silence, compress the audio, send it up to the server. It does language detection, translate to the target language, and then send back the response. And all that has to, round trip time has to be, within 100 milliseconds.
Thank you.
One more.
Do you see some kind of standard emerging where sort of imposed by the Google being the dominant cloud provider? Because everybody knows that everybody has very different requirements for the information. And if you're trying to model sort of the world, which information goes in and which information doesn't, and how do you project that to the different robots?
So I think, for example, Google has been a very large supporter of Wikipedia, and that, even though it has, the problems of, people defacing it, I think has become a very, very useful source of information that's free and everybody can use it. I think, that is something that, Google aspires to help and still support the research community in that regard. But I think a lot of the efforts that are being created around trying to build a knowledge base, open sourcing some of the data sets, that's something I think that we could do more of as a robotics community. Is sometimes we feel that, all we need is more data, and we could actually make a lot more progress. So I think the trend of robotics people publishing code along with their papers, as well as publishing data, is really, really a positive trend, and I hope that continues. And of course, Google will be supportive of that too. We strongly support the open source community, and much of our code is open source, like Android and Chrome and things like that. Yeah.
The final question.
Hi. I would like to see a future where, like, if we teach one robot, that means we teach all of them. So if we teach one robot, like,
Yes.
it means teaching all of them?
Yes.
So what are the key challenges to reaching such a point?
So say the last one.
What are the key challenges to reaching such a future?
Oh, challenges. Yes, that's a good question. So I think that one of the unsolved problems is actually skill transfer. How do you transfer a learned task from one robot to another task? Even the same kind of robot is still hard, because not every robot's exactly the same. I think there's a lot of interesting work that's going on in making robust policies and learning those policies, and being able to basically distill the learning down to what's important about the task and not the robot itself is something I think that would be very important. And of course, there's many, many skills that I'd love my robot to do: cooking and cleaning and helping with office tasks. And as we mentioned before, I think that all of the robots that we're building are tools to help people live better lives, and I really hope that we can see a lot of success in the next decade. And I say next half century, I should say, 50 and more years of Shakey.
Okay, that's a good point to thank James again for this very inspiring presentation. According to the ICRA 2015 app, the next is the banquet, right? At 7:30.